Exponential functions, exponential growth, and decay. So first we need to recall basic exponents. So we have 2 to the negative 1. We know that this one is 1 over 2. The same as 3 to negative 1 is 1 over 3. Now, if we have 1/2 to negative 1, that would be 1 over 1/2. To divide by a fraction means to multiply, so 1 times 2 over 1, which is 2. So anytime we have a fraction to negative exponent, we simply flip that fraction upside down. So this is 2 over 1, which is 2. Now, if we have 2 to negative 2, that means that this is 1 over 2 to the power 2. So this is equal 1 over 4. 2 to the power 2 is 4. Similarly, if I have 4 to negative 2, that would be 1 over 4 to the power 2. 4 to the power 2 is 4 times 4 is 16. Now, if I have 1/5 to negative 2, we can flip it. Negative exponent means flip it, and then we're gonna power it. So this would be 1 over 1/5 to the power 2. So 1/5 to the power 2 is 1/5 times 1/5, which is 1/25. To divide by a fraction means multiply, so it's 1 over 25 over 1, which is 25. This we can simply basically say that this is 1/5 to negative 1 and then to the power 2. So this would be 5 to the power 2, which is 25. As I said before, negative exponent, you just flip the fraction. So that's going to be 5 over 1, which is 5. Now we would like to write square root of 3 as an exponent. So that would be 3 to the power 1/2. Now if I have 7 to the cube root of this, if I have cube root of 7, then we can write that this is 7 to the power 1/3. And here we have all the formulae. A to negative 1 is 1 over A. So this is my first. Then we have a to negative m. It would be 1 over a to the power m. If I have a square root, this is a to the power 1/2. And for any mth root, this equation holds. So that means the nth is on the root's nth root, and m is the power. And this we can either write that this is the m under the root or the m is outside. Now we would have equations to solve. If I have x squared is equal to 15, to solve it for x, I need to take square root of both sides, x squared and square root of 15. If I take square root, it can be positive or negative, so x is equal to positive or negative square root of 15, and square root of 15 should give us, so x is equal to positive or negative 3.87298, or simplifying would be that this is plus or minus 3.87. For part B, before we take square root, we need to first solve it for x cubed. Before we take cube root. So in that case, we're gonna divide by 2, divide by 2. So we have that x cubed is equal to 40.5. And then take cube root. So we're gonna have it, take the cube root of both sides, cube root cube root. So we have that x is equal to cube root of 40.5. This you can either type cube root on calculator or you can use it as an exponent. So that exponent we have right here, or cube root is exponent 1/3. So this we can type it, that would be 40.5 to the power 1/3. So on calculator I'm getting 3.4341, which is approximately 3.43. How do we use it? The calculator, I think we can use the exponent. We can use the exponent button. So some calculate depends on the calculator. Some calculators has it y to the x button, y to the x button. So then you can, if you use this button, you need to put in parentheses 1/3, in parentheses 1 divided by 3. If you have this button, but some calculator has the button that use the power like this. So you could type 4.50 to the power and then in parentheses 1/3, and then you should get the answer what I have here. Similarly, on this one, we would take the sixth root of both sides. So x would be 6 root of 345, or we can write that this is 345 to the power 1/6. So on my calculator, I'm getting that this is 2.6483, or approximately 2.65 if we round it to 2 decimal places. Use remember second place, so I'm looking for the number after. If the number after is 5 or more, we increase the number, so that's gonna be 5. Now a function, an exponential function, is a function of the form f of x is equal a in the exponent. So this is my base. That base needs to be positive and cannot be 1. So this is one of the exponential function. Y is equal 2 to the power x. And let's complete the chart and try to graph it. So first we have it, x is -2, so we substitute -2. So we have y is equal to 2 to the power -2. From the previous slide, we see that this is 2. I'm sorry, that this is 1 over 2 to the 2, which is 1/4. Then we have to -1. So we have y is equal to 2 to the -1. In that case would be 1 over 2. Now we have y is equal 2 to the 0. 2 to the 0 is 1. Then we have y is equal 2 to the power 1. 2 to the power 1 is 2. And then y is equal 2 to the power 2, which is 4. And if we were to graph it, we would use, let's try to graph it. Let me mark this a little bit more straight. So if I mark the units, I'm gonna keep marking from, let me start from 0. 0, I'm gonna mark 1. So I need to mark 0 and 1, that's gonna be my point. And then the next point would be 1 and 2, 1 and 2. And then the next point would be 2 and 4, 2 and 1, 2, 3, 4. And then the points -1 is 1/2. -1 would be 1/2 here. and then the point -2 is 1/4. -2 is 1/4. So the graph looks very close like this. This is the graph y is equal to 2 to the x. This graph has an asymptote at 0. That means the graph is approaching, but it never gonna get to that point. The value of exponent, it would never get to the negative because there is no x when you substitute would give you negative value. Similarly, we're gonna do it for the part B. Y is equal to 1/2 to the x. So we have y is gonna be, we substitute -2 for x. So we will have it 1/2 to the -2. Minus means flipped, and -2 would be 2 to the 2. That gives me 4. Now we're gonna have it y is equal to 1/2 to the -1. Means flipped, it would be 2 to the power 1, which is 1. Then we'll have y is equal to 1/2 to 0. 1/2 to 0 is 1. Y is equal to 1/2 to 1, which is 1/2. And y is equal to 1/2 to the power 2, which is 1/2 times 1/2 is 1/4. And we can graph this function too. I'm going to erase this a little bit, mark it here, so I have a little bit room. Okay, so we're going to start with 0 is 1. It's easier to mark it for 0 is 1. 0 is 1 right here. Then we have for 1 is 1/2. For 1 is going to be 1/2 right there. For 2 is 1/4. So for 2 is 1/4. And for -1 is 2. -1, 1, 2. And for -2 is 4. -1, -2, 1, 2, 3, 4. So the graph looks like this. This is the graph. Y is equal to 1/2 to the power x, and also has the asymptotes at x. So a little bit above the graph should go. So now we have the graphs of the exponential functions. In general, if you have the function that the base is greater than 1, so anything that's 2 to the x, 10 to the x, the exponential graph would go always like this. Always gonna pass through 0 because we have point 0, 2 to the 0 is always 1, 10 to the 0 is always 1, so it's gonna go through this point. And now when the base, this is my base, is less than 1, it's a fraction less than 1, the graph gonna go this way. So that's gonna be this graph. We also gonna go through 0 because 1/2 to 0 is 1, 0.3 to the power 0 is also 1. Now we need to talk about new number. So we know that the number pi is an irrational number and is used to solve problems involving circles. So today we're gonna learn about another rational number. That number is called e. That number is used to solve exponential problems or logarithmic problems with logarithms. Now the number e is defined as 1 plus 1 over n to the power n for large numbers. So the Swiss mathematician Leonhard Euler calculated calculated that number, and that number is called the number E, and sometimes it's called the Euler number. What he did is substitute for large number of n. So if you substitute for hundreds, right here 100, right here 100, calculate that number, that gives you the approximation. Then for larger number 1000, substitute 1000 here, 1000 here, calculate this number, and that's your approximation. For 10,000, you get this number. For 100,000, you get this number, and so on. So this number is calculating, approaches the constant number, called it E. So the E approximation is 2.1782. 17828, all of them has this approximation. So that's why the number E has this larger approximation, and keep going. And simplify, so in simplicity, we're gonna use it, E is equal to 0.7. So it's kind of similar, like we have the number pi, we use approximation 3.14. Even this pi has larger approximation as we keep going. So in similar way, we have the number E, and we're gonna think of it as 2.7. So now number E has the base is E is 2.7. So to graph the function y is equal to E, the base is 2.7 is more than 1, so the graph gonna go this way. And we should have the key button on the calculator E, or sometimes you need to use the second function to get that number. An exponential equation is an equation where the unknown variable x, is in the exponent. For example, 2 to the x, that's the unknown, is in the exponent. Let's call it exponential equation. Another example, 6 to the x is equal. To solve exponential equations, we use properties of logarithms. So the property is exponent property of logarithm that says log of y to the power x, that x can go in front of the log. That's the property of the logarithm, that this x can be multiplied to the front x log of y. And that's how we're gonna keep solving the logarithmic equations. So the first equation can be solved in two different ways. We have 2 to the power x is equal to 4. We can write that the 4 is, so we would have 2 to the x is equal, 4 can be written 2 to the power 2. So then I can simply drop the bases, equate the exponent. So it would be that x is equal to 2. If I just equate the exponents, right? Equal the exponents. Another way to solve it is to using the logarithm property of the logarithms. So using this property. How can we do it? If we have 2 to the x is equal to 4, we can take the log of both sides. So it would be 2 to the x is take log of both sides. And then using the property of logarithm, this exponent can go in front. So this would be x times log base 2 of 2 is equal to log 4. And then to solve it we would divide log by log 2, divide by log 2, this cancel out, and if you type on calculator, that should give us the value of 2. If you type on calculator log 4 divided by log 2, you should have on scientific calculator, we have the log button, so you can easily use the log button. It should say log, and you simply punch the log of 4. So the first equation we could use in two different ways, because we could write 4 as 2 to the power, so we could find the same base as what we have on that side. This equation, part B, 6 to the x and 10, we cannot find the same base. There is no 6 to what exponent would give us 10. There is no such exponent. So if you cannot find the same base, the only way to solve it is use the log property. So in that case, we take log of both sides. So log 6 to the x is equal to log of 10. Then by the property of logarithms, the exponent can go in front. So we're gonna have x log 6 is equal to log 10. And as before, to isolate for x, we would divide by log 6. Log 6 is cancelled out. So my x is equal to, you type on calculator, log 10 divided by log 6. And that should give us 1.285097. And if we round it to 2 decimal place, would be 1.29. To 2 decimal place, we look for the next digit. If it's 5 or more, we increase that digit. For part C, before we take log of both sides, we need to solve it for the exponent. So 5 to the x. So first we're going to divide by 2. Divide by 2, divide by 2. This cancel out. So we have 5 to the x is equal to 12. And then we can take the log of both sides. So log 5 to the x is equal to log of 12. By properties of log, this exponent can go in front. So we have x times log 5 is equal to log 12. To solve it, we would divide by log 5. So then we have that x is equal to, type on calculator, log 12 divided by log 5. And that should give us 1.54399593. So if we round it to 2 decimal places, 1.54. Example 3. Price P in dollars of Honda Civic sedan that is X years old is given by this equation. So we see it's exponential. X is in the exponent. How much does the 3-year-old Honda Civic cost? So X is my how in years, how old is the car. So in that case, we substitute 3 for X. So part A, we have P would be equal 242250 times 0.90 to the power 3. And make sure you know how to type this on calculator. That P would be equal to, if I calculate this correctly, 17678.25. So 3-year-old Honda Civic sedan would be 17,678.25. For part B, how much does 9-year-old Honda Civic cost? That would be part B. We substitute 9. So P would be equal to 24 0.90 to the power 9. If you type all of that on calculator, I'm getting the number 9,390. 9,395 4.94685. So we always round to the nearest cents. So to the nearest second, to the nearest 10, to the nearest hundred, second decimal, to 2 decimal places. So the price is 9,394.95 cents. Example 4. The number n of bacteria present in a culture at time t is in hours is given by this formula. So t is in the exponent. What is the population after 4 hours? So that 4 hours, what does that mean? That means that time. So we substitute 4 for time t. So we have a n is equal to 1000 times 3 to the power 0.01 times 4. So first we multiply 0.01 times 4. So n is equal to 1000 times 3 to the power 0.04. And then we punch it on calculator and we should get n is equal to 1000 times, I'm getting 1.04492432,351 times 1000. You can type everything on calculator. That should give us 1044.92351. And because we're talking about number of bacteria, we cannot have 0.9 of bacteria, so we round it up to the whole bacteria. So n is equal 1045 bacteria. After 4 hours, there are 1045 bacteria. Part B. The question asks, when will the number of bacteria double? So how many bacteria was at the beginning? At time 0, we can check it first. So if I substitute 0 for time t, we will have 3 to the 0.01 times 0. If I substitute 0 for times t first, 0 times anything is 0, 3 to the power 0, so that whole stuff would be 1. So 1 times 1000, at time 0, we had 1000 bacteria. So now it needs to double. What does it mean double? Double would be twice. So we would have that my n would be 2000, right? Double times 2. So we will have equation 2000 is equal to 1000 times 3 to the power 0.01 and t. One more time. First, I'm looking at the number of bacteria at time 0, how many was at the beginning, because then we're gonna double that amount. So at the beginning, I substitute 0 for t. So 0 times 0.1 is 0. So 3 to the power 0 is 1. 1 times 1000, that's my 1000. So if initially was 1000, to double would be 2000. And that's my n for n bacteria. And then we need to just solve that equation. So first we get rid of this 1000. We're gonna divide both sides by 1000. This cancel out. This reduces to just 2. So we have 2 is equal 3 to the power 0.01 and t times t. So then we can take log of both sides. Log of 2 is equal log 3 to the power 0.01 times t. So then by the properties of log, this whole exponent can go in front. So we're gonna have it log 2 is equal 0.01t times log 3. Then we would divide by log 3, divide by log 3. This cancel out. You can type on calculator, what is this log 3? When I type it, I'm getting 0.63092975, and this is equal to 0.01 t. Then we can divide it by 0.01, divide by 0.01, this cancel out, and we getting time t is equal to 63.09229. So t is approximately 63 hours. How long would it take for the bacteria to double? Approximately 63 hours. Example 5. The size P of a certain insect population at time t in days is given by this formula. Determine the number of insects at 20 days. When will the insect population reach 800? So the first example, part A, we simply finding P at 20. So as time t is 20, we substitute 20 for the time t, and then we simply enter this into calculator. So we have 500 times 2 to the power 0.03 times 20. So p at 20 is equal to 500 times 2 to the power, and if I multiply this 0.03 times 20, I'm getting 0.6, and then we can enter this into calculator, and we getting P 220 is equal to 500. If I type on calculator 2 to the power 6, I'm getting that this is 1.51571 something, and then if I multiply this time 500, I'm getting 20. I'm getting that this is equal to 757.8582, and because this is a number of insects, right? So we cannot have 0.8 insects, so we're gonna round it up, that this is 758. So this is 758 insects. For part B, my 800 is the insect population, so this is equal to 800. So we had that 800 is equal to 500 times 2 to the power 0.03 t. Then to solve it, we need to first divide it by 500. So both sides divide by 500. Divide by 500. This cancel out. And 800 divided by 500 is 1.6, is equal to the power 0.03 t. In order to take t, in order to bring this exponent down, we take the log of both sides. So we have log of 1.6 is equal to log of 2 to the power 0.03 t. And then by the properties of logs, this exponent can go in front. So we had that this is log 1.6 is equal to 0.03 t log 2, and then we can divide this both sides by log 2, divide by log 2, these logs cancel out, and if I type this on calculator, I'm getting 0.67807 is equal to 0.03 t, and to solve it for t, we would divide by 0.03, divide by 0.03, this cancel out, and I have that t is equal to 22.6, and the time is in days, so it's 22.6 days. Time is in days, so 22.6 days. Example 6. A colony of certain small organism grows according to the function, this function given with the E number, measured where P is measured in grams and T is days. What is the initial amount of small organisms? So initial amount would be T equal to 0. So we substitute T equal to 0 to that equation. So we have it that P at 0 would be 100 e to 0.045 times 0. 0 times e to 45, so P at 0 is 100, e to the 0 is 1, so it's 100. So the initial amount is always this number standing here in front. Now, what is the population after 4 days? So we're gonna have P at 4. It's gonna be 100 e to the 0.045 times 4. First multiply times 4. So we have P at 4 is equal to 100 e to the 0.18. Then we can type on calculator. P at 4 is 100 times 1.197217, and times 100, P at 4 is 119.72 grams. For part C, the question asks how long will it take for population to reach 150 grams. So now 150 is my P for population. So we have 150 is equal to 100 e to 0.045 times t. So as before, first we need to divide by this 100. So both sides divide by 100, divide by 100. So we have 1.5 is equal to e to 0.045 t. Now we can take log of both sides, or we can take ln, natural log. But let's take log of both sides. 1.5 is equal to log of e to 0.045 t. As before, the whole exponent can go in front. So we have log 1.5 is equal to 0.045 t times log of e. We can divide both sides by log e. This would cancel out. And if I divide this, 0.405465 is equal to 0.045 t. We can use, instead of e, we can use 2.7. That might be easier to calculate. And then later we divide by 0.045, 0.045. This cancel out. So my final answer would be that T is equal to 9.01. So in other words, 9 days. Example 7. A remaining mass m of a 10 kilogram sample of radioactive substance after T days is given by this formula. How much of substance will be left after 20 days? We take 20, substitute for T. So part A, m at 20 is equal to 10 times 0.5 to the power 20 over 100. 20 divided by 100 is 0.2. M at 20 is equal 10 times 0.5 to the power 0.2. So M at 20 is equal to 10 times, if you perform the power, use the y to the x key or the power key, and I'm getting that this is 0.87055. So times 10, m is equal to 8.7055. So in other words, m is equal 8.7 kilograms. The mass is in kilograms in kilograms. For part B, we have how long will it take for the mass to decay to 0.4 kilograms. So now my mass is 0.4. So we have 0.4 is equal to 10 times 0.5 to the power t over 100. As before, first we divide by 10 to cancel this out. So we have 0.04 is equal 0.5 to the power t over 100. Now we can take log of both sides. So we have log of 0.04 is equal to log of 0.5 to the power t over 100. As before, the exponent can go in front. So we have log of 0.04 is equal t over 100 log of 0.5. Then we will divide by the log of 0.5. This cancel out. If we type this on calculator, we getting 4.64386 is equal t over 100. So to solve it for t, we would need to multiply times 100 times 100, and we getting that this one is 464.4 years is equal to t. So for a radioactive decay to get to 0.4 kilograms, it takes 446 years for the radioactive sample to decay.